So now we are finally at the content part of this chapter. We're going to start with the simplest situation, single layer for a slab, and many practical situations can be approximated as a slab. That's why we even bother to do a slab like that. Okay, so it can be a layer of clothing, it can be a building wall or a window glass or that silicone insulator I talked about. All of these we may be able to approximate as a slab with a high temperature on one side and low temperature on one side. So this is my axis x, and x equal to 0 I have T1, and x equal to L I have T2. So then I now try to develop the governing equation and boundary condition for this situation. So we always start from the most general equation in the correct coordinate system. So in this case, of course, the coordinate system is Cartesian. So in the Cartesian coordinate system, this is my energy equation, and this is for all situations. This isn't the equation that we need for the slab with no heat generation. We're going to have to simplify this. So how do you simplify that? We drop these terms because this one is dropped since it's at steady state. This one is dropped because there is no bulk flow through this. So there can be flow here, there can be flow here, but important thing is our domain of computation, the domain that we're interested in is here, and inside these there is no flow. So that's why this term is dropped, and we assume there is no heat generation, so this term is also dropped. So that gives us the governing equation as simply d squared t dx squared equal to 0, and this is going to need two boundary conditions. Why? Because it's a second order equation. We'll see in a second more explicitly, but the two boundary conditions are temperature here is given and temperature here is given. Note that from a physical sense, there is no way you can get how temperature varies inside these if you do not know the boundary conditions. So these very much have their physical counterpart. So now we will try to solve this, and so here I will go slowly. So first I integrate once to get dt dx equal to c1, and then I integrate again t equal to c1x plus c2. Notice that we have two unknowns, c1 and c2. So to solve for two unknowns, we need two equations. Those are the two boundary conditions. So using the boundary condition, the first one, t at x equal to 0 equal to t1. So if I plug in x equal to 0, then I get t1 equal to c2. And then if I use the next one, t at x equal to L as t2, so then I plug in for L, for x equal to L, so t2 is equal to c1L plus c2. So I have two equations now that will solve for two unknowns, c1 and c2. So c2 is already solved. So c1 from this equation, c1 is t2 minus c2 over L, or equal to t2 minus t1 over L, and then I plug this back in my equation. So I plug in for c1 and c2 to get the final equation. Now, as soon as you get this equation, we should always check whether we made algebraic errors, or is this indeed true. And the most obvious thing to check is to make sure that this indeed satisfies the boundary condition. So if I plug in x equal to 0 here, then I get t equal to t1, right? And if I plug in x equal to L in here, then I get t equal to t2, which are my boundary conditions. So indeed it satisfies the boundary conditions. Okay, so this temperature change is linear. And let's look at a little bit, well, let me come back to this. So we have the temperature profile here, and then we have heat flux. So how do you calculate heat flux? Remember, heat flux, or in this case I'm calculating heat flow. So heat flow is equal to minus k dt dx times the area. Okay, so dt dx, so if you take the derivative here, dt dx is equal to t2 minus t1 over L, right? So I plug in for dt dx and I get this quantity Ka T1 minus T2. So this is the heat flow. You notice that this heat flow is a constant. So amount of heat flowing through any of these layers, whether it's here or here, it's the same heat. Why? What is the physical reason for this heat flow to be constant? Because suppose I think of a layer like that. What will happen if more heat comes in than goes out? That means the temperature of this region will increase over time, but that is not allowed in steady state. So the amount of heat coming in has to be equal to the amount of heat going out, and so the heat flow has to be a constant from a very physical standpoint, and that's exactly what you see mathematically because this quantity is a constant. Now, I can also write this same equation this way. Qx is equal to some temperature difference divided by L over Ka. So Qx is the heat flow, is the amount that flows, and then T1 minus T2 is sort of the driving force. It's the temperature difference that's driving the heat. So if flow is equal to some driving force divided by a quantity, what do you think would be the likely interpretation of this quantity? Because more this quantity, higher this quantity, less heat will flow. So this must have to do with resistance. So this we call thermal resistance. So L over Ka is the thermal resistance of a slab. Okay, and just one last comment. You notice that the heat flow is kind of linear with thermal conductivity. So if we think of two situations, one here where you have warm tissue, cold tissue, and in between it's not something else. Let's say it's just tissue. Now tissue has a thermal conductivity of something like this, about 0.5, and whereas suppose I replace this tissue part with some silicone insulator that has much lower thermal conductivity, then the formula shows that the heat flow this way is going to be reduced linearly. So if 0.15 is like almost 1/4, so the heat flow this way would also be 1/4, which means the um, the rectal tissue will not get cooled down as easily, so its chances of freezing would be reduced.